You really gonna do that to me? You really gonna that big? Okay. So we're just gonna kind of go through this pretty quickly. I think I don't think there's gonna be too much in here that's like shocking. But 5.2 is about the characteristic equation. Remember last time we talked about just finding. How did we do it before? I guess. How did they have us do it before? Or did they just define it? No, yeah. So in 5.1 they just provided eigenvalues and they said find the eigenspace, which was simply construct that matrix and find the null space of that matrix. So that was the whole thing, right? And then they had some theorem about the triangulars. Oh, then this was an important theorem. Okay, so it was introducing theorems, but it didn't say. Okay, yeah. 5.3 is going to be important though. 5.3 is what we're going to do. So let's just get through. And I think we did do a number of problems from this. All right. So useful information about the eigenvalues of a square matrix A is encoded in a special scalar equation called the characteristic equation. All right, so finding the eigenvalues. Remember, we construct this matrix A minus lambda I, and we are trying to find the non-trivial, solutions of this. By IMT, this problem is equivalent to finding all lambda such that the matrix is not invertible. By theorem 4, this matrix fails to be invertible precisely when its determinant is 0 because you're squashing a dimension. So like the size of a line in the plane is 0. That's what that really means. So so this is the formula for the determinant. So if you compute this determinant, you get something as a polynomial in lambda. The determinants in example 1 transform the matrix, which involves two unknowns, lambda and x, into a scalar equation, which involves only one unknown. Yeah. Okay. Before turning to larger matrices, recall that from section 3.1 that the matrix Aij is obtained by deleting the. Oh, geez. Okay. Are we really going to do more of these minors? The determinant of can be computed by the expansion across any road. I totally forgot this formula, man. Is that a thing? Do we really want to go back to here and just like okay, these are nice. Oh. Oh, I forgot about this. Yeah. I forgot about that. Yeah. That if you scale a row, it scales the determinant. If you switch a row, it switches the sign of the determinant. And if you do a row replacement, it doesn't do anything. Right. Yeah, this is a good one actually. I like this one. The number 0 is not an eigenvalue of A if and only if A is invertible. Because what that means is that you get this A minus, which is just equal to A. So that means that the determinant was already 0, or that there was a non-trivial null space. All right. The characteristic equation is just this. If and only if lambda satisfies this characteristic. All right, find it. We're not finding it, bro. Expand the product. If you want to verify lambda as an row reduce A minus lambda I. If you get a pivot in every column, something is amiss. Right. The scalar lambda is not an eigenvalue of A if that's the case. Looking back at example 3, notice that all have at least one column without a pivot. Cool. All right. Is a polynomial the determinant is a polynomial in lambda. It can be shown that if A is an n by n matrix, then the determinant is a polynomial of degree n. Let's see, how's my volume? My volume okay? Maybe a little bit more. The eigenvalue 5 in example 3 is said to have multiplicity 2. The algebraic multiplicity of an eigenvalue is the multiplicity as a root in the characteristic equation. Okay. Because the characteristic equation for an n by n matrix involves an nth degree polynomial, the equation has exactly n roots, counting multiplicity, provided complex roots are allowed. Such complex roots, called complex eigenvalues, will be discussed in 5.5. Until then, we consider only real eigenvalues. The characteristic equation is important for theoretical purposes. In practical work, however, eigenvalues of any matrix larger than 2 by 2 should be found on a computer, unless the matrix is triangular. All right, good. The next theorem illustrates one use of the characteristic polynomial, and it provides the foundation for several iterative methods that approximate eigenvalues. If A and B are n by n matrices, then A is similar to B. What? Okay. If A and B are n by n, then A is similar to B if there's an invertible matrix P such that P inverse A P equals to B. So B is similar to A. We say simply that A and B are similar. Changing A into P inverse AP is called a similarity transformation. I've never heard of that before, actually. I don't even. Okay, so wait, all right. A, B, n by n. If P invertible, and P inverse AP is equal to B, then A is similar to B, and notice this is, what is it called? Symmetric? Symmetric? Okay. So similarity, if two, and they have the same characteristic polynomials. Oh, really? So are they simply permutations, or what does that even mean? I wouldn't have guessed that's necessarily the case. So similarity. So what the hell do these even do? Well, I don't get why this is the case. So they're saying B minus lambda I. Okay, so first B is equal to P inverse AP. Okay, we have that. Then B minus lambda I is equal to P inverse AP minus lambda P inverse P. But why? Oh, because this is the identity? Why are you writing it like that? Yeah, this is the identity. Okay. So, oh, then you factor out P inverse. Okay. This is I. So that's chill. So then you factor out P inverse. And you get AP minus lambda P. And then you could factor out P. So you get P inverse A minus lambda I times P is equal to B minus the Oh, so since you're able to make it A minus lambda I, then so this is the proof that if A, B are similar, then they have the same car poly. Okay. Using the multiplicative property in B in theorem 3, we compute that the determinant of this is equal to the determinant right. It's equal to this times this times this. Therefore, since this is equal to 1, then we can prove, so then by det AB equal to det A, det B, then we're going to get det of B minus lambda I is equal to det P inverse det A minus lambda I det P. But then this is equal to det P inverse P equal to 1 times det A minus lambda I. So then, okay, so that's that. Note, similar implies same car poly, i.e. eigenvals, but same eigenvals does not imply similar. So it's only in one way. Similarity is not the same as row equivalence. But row operations change eigenvalues. So that's pretty neat. I don't think I've seen that proof before. Eigenvalues and eigenvectors hold the key to the discrete evolution of a dynamical system. Okay, let A be this matrix, which looks like a population type thing, because at the very least, it's like a Markov matrix, right? Is that what they call it? They call it a Markov matrix, right? They call it a stochastic matrix when a left stochastic matrix is when these are weird. These are weird. Doubly stochastic matrix. I'd like to look into that. That's pretty interesting. Okay, so analyze the long-term behavior as k increases of the dynamical system with initial condition 0.6 and 0.4. The first step is to find the eigenvalues of A and a basis for each eigenspace. So we get our characteristic polynomial, then we use the quadratic formula to find our eigenvalues. Then they just give us the eigenvectors. They don't go through the whole thing of solving it because they just tell us. The next step is to write x0 in terms of v1 and v2. This can be done because v1 and v2 are a basis for R2. Why? Because they're not multiples of each other. So there exist weights C1 and C2. So x0 can be written as a linear combination of the eigenvectors. Okay. So wait, how did they get this? Oh wait, this is the okay. This is the yeah. Because v1 and v2 are eigenvectors of A of A. Oh yeah, right. Okay, and yeah, it's okay. We can compute each xk. So okay. All right, that makes sense. Yeah, so you basically you just start applying matrix powers, but the thing is the matrix powers just turn into these powers of eigenvalues, but this one doesn't. This one's eigenvalue is 1, so it doesn't even change. And that allows you to find what xk is really easily. Right. So in this case, because the powers of 0.92 go to 0, it tends to 0.125 times. Okay. And this is the steady state. That's pretty cool, actually. Mathematica and Maple can be used for symbolic calculations to find the characteristic polynomial, but there's no formula or finite algorithm to solve it for. Okay, so they're just saying the quintic. The best numerical methods for finding eigenvalues avoid the polynomial entirely. MATLAB finds the characteristic polynomial of a matrix by first computing the eigenvalues and then expanding the product. Several common algorithms for estimating the eigenvalues of A are based on Theorem 4. What was Theorem 4? Similarity? Really? The QR algorithm is discussed in the exercise. Another algorithm called Jacobi's method works when A is symmetric and computes a sequence of matrices of the form. Each matrix in the sequence is similar to A and so has the same eigenvalues. The non-diagonal entries of 10 to 0 as K increases, and the diagonal entries tend to approach the eigenvalues of A. And the diagonal entries tend to approach the, okay. Yeah, because I do want to know some of the numerics. Like, I have no idea. Wait, find the characteristic equation. All right, should we just... I mean, like, let's read through the I mean, come on. You know, it's like, do we really, need to do that? I don't think so. I think we've done enough of that. No, we're not doing that. I'm sure that it's nice to know, but like, really, I'm gonna use a computer. Hey, what's up, man? What's up? Dude, I'm beat, man. I just ran 7.5 miles. I'm tired. I'm trying to get to a half marathon, dude. I really want to do a half marathon, but whenever I get to like 7.5, I'm out. I'm done. I gotta walk home. I'm so tired. But then once I like get a little bit of food in me, I drink some water, I'm like back. I'm like good. Except I definitely couldn't run again. Like I'm out for the rest of the day. I'm not running at all. All right. List the eigenvalues with their multiplus. Okay. Yeah, this section is like a bunk-in section. We'll do the true false, I guess. It can be shown that the algebraic multiplicity. Is always greater than or equal to the dimension of the eigenspace corresponding to lambda. That's actually kind of interesting. All right, 18 looks actually pretty good. Find H in the matrix A below such that the eigenspace for lambda equal to 6. Oh, but then we're going to get, okay, so if you do that, this is going to be 3, 3, and this is, H is 9. I'm going to guess H is 9. But we'll do that. That actually sounds pretty fun. All right, let 19. Let A be an n by n matrix and suppose that A has n real eigenvalues repeated according to their multiplicity. Explain why the determinant of A is the product of the n eigenvalues. Explain why the determinant is the product. Yeah, we'll do that. I don't know. Let me think. Use the property of determinants to show that all right, 20 seems pretty good. I guess there are some good ones in here. All right, 21 through 30. Oh, here we go. Here's some good stuff. A widely used method for estimating eigenvalues of a general matrix is called the QR algorithm. Under suitable conditions, this algorithm produces a sequence of matrices all similar to A that become almost upper triangular with diagonal entries that approach the eigenvalues of A. The main idea is to factor A or another matrix similar to A in the form A is equal to Q1 R1, where the transpose of Q... Whoa. What? The transpose is equal to the inverse? Wait, that's so weird. Imagine A transpose equals A inverse. What does that even mean? That means that, like... That means that A times A transpose is equal to I? That's weird. That's weird, man. And R1 is upper triangle. The factors are interchanged to form A1, which is equal to R1 times Q1, which is again factored, and so on. The similarity follows from a more general result. Show that if A is equal to QR with Q invertible, then A is similar. Show that if A is equal to QR and Q is invertible, then A is similar to A1 equal to... Wait, what? I don't even understand. Oh, wait. I don't even understand. Oh. See, this is QR and this is RQ. We'll do that one. All right, this is going to take longer. Dude, all right. I kind of wanted to just not do this, but that's fine. So we have to do 5.3, and 5.3 I feel like is going to be important. Okay, I got a bunch of homework, man. Isn't this just in the... We'll do 32, but I think that 32 is just in the, maybe I'll get my iPad, I'll do it on the whiteboard. That'll be fun. I haven't done a whiteboard thing in a while. I'll get my iPad and we'll do that. Construct a random integer valued 4x4 matrix A and verify that A and A transpose have... Okay, we're not going to do that. We're not going to do any of these. Okay, so I got my problems. I got a brand new freaking whiteboard. Okay. Um, all right. Look at that. Look at that, man. That looks good. That looks really good. Yeah, man. All right. Cool. All right. So 18 through 32. All right, so 18 is we have this matrix 6, 3, 9, minus 5. Zero, zero, 6, 8. Fine. Eigen space 6. We get minus 2. Is it any of it visible? It seems like it's cut off just a tiny bit. Okay, so wait, we're gonna do this one on the computer though, because it's much more amenable to computer, whatever. So we just gotta write out this matrix. So 6, 3, 9, minus 5. 0, 9 at variables. H. I don't know if we want to actually do this. I think I just want to Okay, so we have this matrix. But what we want to do is we kind of want to just... So the problem is, I wonder if this works. Yeah, I figured it wasn't going to work. So first off, we need to do a minus 6i. Okay? So, but I want to duplicate this. I want to duplicate this to be... So I'm going to guess that this needs to be 9. Then we're going to do a minus 6I. Or in rather, okay, so the null space is dimension 2. But what we could do is we can compute the rank, and the rank is 2. Okay, so it's 9 because then you create a you create a dependence. All right. Yo, what's up, Cheese Man? It's fucking Cheese Man in the building. Um, all right. So I think I get it. I mean, okay. So if a n by n and we and that a minus lambda I is equal to lambda is equal to product of lambda I minus lambda for I 1 to n. Then det A is equal to prod lambda I, but why? My naive picture is that for 2D, the parallel pipe head sketched out by A on the eigenvectors. But the thing is, the example that I did was only the example that I did here was it's the one in the bottom right, the small one with x1 and x2. The thing about this is it is true that they are not parallel, and you are guaranteed that. Well, I guess we didn't cover multiplicity, but I think if wait, multiplicity is actually really interesting because can you have two eigenvalues, or can you have two eigenvalues that are the same but have different eigenvectors? Yeah, you can. Yeah, you can. So in that case, so the algebraic explanation is oh yeah, that's so much easier. That's a way simpler way. Right. And the thing is, and those are orthogonal, so it doesn't even it's like diagonal matrices rule, man. But the thing that's weird to me, oh yeah, no, that's fine because they're orthogonal. Okay, that was a pretty good problem. I like that one. So yeah, so the easiest way to think about why if you have the characteristic polynomial that the determinant of A itself is just going to be the product of the eigenvalues is you just plug in for, I mean, because you know, you've assumed, you know that this is going to be like this for these distinct eigenvalues. Therefore, if you just plug in lambda equals 0, then this just becomes the product of the eigenvalues is equal to the determinant of A. And we know that this is true okay. Yeah, that checks out. I like the geometric way more, though. Okay, let's see. What else do we have to do? We're doing 20 now. I'll skip 20. 20 is not that fun. All right, let's do the true falses. But true falses we don't do on the board. Let me get my paper, though. All right, 21. If 0 is an eigenvalue, then A, that's, okay, 21 false. If 0 is an eigenvalue, then think about it. That means you have A times X is equal to 0 times X. Okay, but that means that there's a non-trivial solution of AX is equal to 0, because 0 times X is 0. Oh my god, that's so obnoxious. All right, the 0 vector is in the eigenspace of A associated with an eigenvalue. Yeah, of course, that's true. Because the eigenspace is a subspace, it's got to have 0. Maybe that's actually a bad way to answer that, but it is the easiest way to answer that. A matrix A and its transpose have different sets of eigenvalues. That's false. The matrices A and B inverse AB yeah, that's true. You just apply say actually let me try to think about that. All right, so take det A. So we have det A. That's fine. Now we take det B inverse A B, which is yeah. So that is true. That is true. All right, 25. If two matrices have the same set of eigenvalues, then they're similar. That is false. If two matrices have this, wait, oh, I did the wrong one. Oh, I did the wrong one. Okay. If 2 is an eigenvalue, then A minus 2i is not invertible. That's true. Because it's going to have an, because that matrix A minus 2i is going to have a non-trivial null space. Because that's what it means to be an eigenvalue, right? Wait, hold on. A x equals lambda x. So we have A x is equal to 2x. Then we're going to get A minus 2i. Yeah, and because eigenvectors have to be non-zero. So yeah, 25 is true. 26 is false. 27, if lambda plus 5 is a factor of the character, wait, then 5 is an eigenvalue? No, what? That doesn't even make sense. It's going to be minus 5. The multiplicity of a root R of the characteristic equation of A is called the algebraic multiplicity of R as an eigenvalue? I forget what they call it. Where do they say this? You know, I wonder where the name root came from. Where did the name root come from, man? That's pretty interesting. Okay. I wish I knew Latin. I feel like it'd be pretty sick to know Latin. Okay, so I don't know 28. The multiplicity of a root r of the it's called the algebraic multiplicity of r as an eigen. I think that's true. I didn't see anything really wrong with that, but I don't know. 29. The eigenvalue of the n by n identity matrix is 1 with multiplicity n. That's true. 30. A matrix can have more than n eigenvalues. Matrix A can have more than n eigenvalues. That's false. Okay, so let's get the answers. The last time I renumbered it, it was really annoying. Oh, that's so cool. The convex hull of the permutation matrices. Yeah, man. That's pretty cool. The convex hull of the permutation matrix. Actually, I don't know if I quite... But I can see how... I can see how permutation matrices and doubly stochastic matrices are really similar. Dude, that seems really fun. Okay, 21 is false. 22 is true. 23 is false. 24 is true. 25 is true. 26 is false. 27 is true. Oh, but you know what? I think it see, this is lambda minus 5, but this is lambda plus 5, so it's actually false. 28 true. 29 true. 30 false. Okay, cool. Yeah, you gotta be careful. It transcribes some of the math wrong. All right. Okay, if A is equal to QR, then A is similar to, so that means that QR is similar to RQ. Therefore, we can write like P inverse QRP is equal to RQ or something like that. But I don't know how to show it. So the definition of similar is that you can write A is similar to B if there's an invertible matrix P such that P inverse AP is equal to B. And how do you show that they are similar? Do you have to use that Q inverse equals Q transpose? Okay, wait. The main idea is to factor A in the form A is equal to Q times R, where Q transpose is equal to Q inverse. And R is upper triangular. The factors are interchanged to form A1 equal to R1 Q1. Just factored again as A1 equal to Q2 R2. Then to form A2 is equal to R2 Q2 and so on. The similarity follows from the exercise in 31. But I think 31 doesn't, you don't need to use the triangularity of R and the whatever it's called. Is this property the property Hermitian? I forget. What is it called when the matrix transpose is the inverse? I'm pretty sure it's called Hermitian. Oh, it's called orthogonal. It's called orthogonal. Bro, it's so windy out. Okay, I know this is easier than I think it is. I don't know why I'm like tripping out. Oh, you know what, actually? wait, we have QR is equal to RQ. Let's multiply both sides on the right by Q inverse. No, wait. On the left by Q inverse. So we're gonna get Q inverse QR is equal to Q inverse RQ. So then R is equal to Q inverse RQ. That doesn't help me at all though, because you know what I think you need to do is maybe if you do oh, there we go. Wait, I think I got it. So this is a. Oh wait, no, damn it. I don't know how to do it. If you have or maybe you can do like Q inverse QR is equal to Q inverse QR. Dude, I don't know how to do it, man. I really don't. How do you do it? Oh. Yeah, you just apply Q inverse AQ and then it cancels out. Oh, okay. So if you have A is equal to QR and A1 equals RQ, and you do Q inverse AQ is equal to Q inverse QR. Q. So then, yeah, so then Q inverse AQ is equal to RQ. Therefore, A similar RQ. Okay, I don't know why. I knew it was going to be just apply the thing. It's never as complicated as I thought. So that if A and B are similar, then the determinants are equal. Oh, this is the easy one. This is literally in the book. You just okay, if they're similar, then they have the same determinant, right? Here. But you don't even have to do this. You could just do what is it? Let's do this problem. This problem is even easier than that. Okay. A is equal to or let's do this. P inverse A P is equal to B. Then we apply det to both sides. Then we're going to get det P inverse times det A times det B, or P is equal to det B. Okay, but then since determinants are commutative, because it's just multiplication on the reals, then the determinants P and P inverse cross out, and then you get det A is equal to det B. Okay, so that is, damn, 3430. So annoying. All right, let's hurry this up, I guess. We're gonna do diagonalization. So I am gonna restart the stream in a second.